So let's talk now about how we attempt to deal with confounding factors when we're looking at studies. We really have two essential choices. We can deal with it on the design side or on the analysis side. We've seen that you can stratify to deal with it in the analysis. Now we want to think about the effects of study design on confounding factors. So just to recap where we were, case control studies can have huge problem with confounding factors. We saw this with the moped studies where the drivers were a lot more likely to be wearing a helmet than the passengers. Similarly, cohort studies can have huge issues with confounding factors. We saw that with organics and allergies, where tobacco smoke was a huge confounding factor. And in both of these cases, the exposed group and the unexposed group have lots of other differences, in part because just people making whatever choices they make. And the sorts of people that choose to eat organics are different from the sorts of people that choose to not eat organics in all sorts of other ways. So what's the other study design that we have? Well, let's think about randomized experiments. And specifically, I want to think about the difference between cohorts and randomized experiments. So let's start with another example. How about this question? Does stretching before you run help to prevent injuries? And I will say, back when I was younger, it was just axiomatic. You stretched before you ran, otherwise you were going to hurt yourself. That's what everybody said. So is that actually true? And over time, people have actually come to believe that it isn't. So before we move on, I'd like you to go to the Google form and just thinking about this question in general, maybe from a cohort study, I'd like you to describe two potential confounding factors that might come up if you were studying this. And like we did for the organics and allergies, what effect those confounders would have on the result. And briefly, sketch what the design would be of a randomized controlled experiment to address this question. Okay, welcome back. So here's a couple of confounders that I thought about. One might be, what if somebody had injured themselves in the past? So somebody with a prior running injury might be more cautious and thus more likely to stretch first because they're being careful to try to avoid re-injuring, yet at the same time, that person with a prior injury probably is more likely to have another injury because you're often not as strong after an injury. That joint or whatever might still be a little bit fragile. So that would lead it to look like people who stretched have a higher rate of injuries than is actually the case because of this confounding factor of the prior injury. Another one might be people who have had a lot of education in running technique, maybe good coaching, or maybe they've read a lot or something like that. And those people who've had a lot of education in running technique might well have been told to stretch and might be more likely to stretch first. And also a good technique probably goes with a lower rate of injury. So that technique education would make it look like stretching was associated with fewer injuries, where again, actually it could be this confounding factor. And when you correct for it, you would then see less of a protective effect for stretching. So as we see, confounding factors can adjust our association in a lot of different ways. Now, I want you to think, how would you design a randomized experiment to address this question? You actually already answered that on the Google form. So in this case, you would need to randomly assign people to stretch or not. I want to emphasize, you can only do this if you actually don't really think stretching helps. This has been done. The studies I'm aware of did it with Australian military recruits. So you had several different platoons who were going to go out running, and one platoon was being told to stretch first. The other platoon did some arm exercise things. So they also had some warm up, but it wasn't stretching the running muscles. And then they measured injury rates, and military groups are great because you can kind of tell them what to do. So in that case, where people are randomly being assigned to stretch or not, does this change our confounding factor picture? I want you to think about that and go record any thoughts you have on our class form. Okay, so the prior injury, somebody who has a prior injury is still more likely to have a new injury. You're still going to see associations between the confounding factor and the outcome. You can't prevent that. This is really just saying people are different. You don't want to make them all the same. So that association is still going to be there. If you make them all the same, then you're not going to be collecting data on people with prior injuries, and your results are not going to be as interesting. They're not going to be as generalizable. On the other hand, this association, this association is not going to hold anymore. Earlier, we had said people who had injured themselves might be more likely to stretch first because they were worried about re-injuring, but they are no longer making the choice. Once we are randomly assigning people to stretch or not, we are breaking that association. All of a sudden, there's no systematic difference between my exposed group, the people who stretch, and my unexposed group, because it's not their choice, because it was just a coin flip that decided whether they stretched or not. And breaking that link means that prior injury is no longer a confounding factor. And that's huge. So randomized controlled experiments don't have confounding factor problems because the association between the exposure and the potential confounder is broken. So that's one of the big ways we deal with confounding factors when it's possible. I've got a slide now that just summarizes the many ways people deal with confounding factors. In the design of the study, you could restrict it. You could say, okay, this study is only looking at smokers. Not a confounder, we're only finding out about the results among smokers, or only looking at helmet wearers, or only looking at people with prior injuries. That means you can't generalize your study to as large a population. It's only going to tell you about the health effects on smokers, but it's getting rid of that confounder. You can do more sophisticated things with matching, particularly in a case control study, where for every smoker who is a case, you make sure you have a smoker who is a control. For every helmet wearer who is a case, you have a similar helmet wearer who is a control. If you're doing a matched study like this, then you have to do some special things in the analysis, but it is something people do. Or when it's ethically and practically possible, you can do a randomized controlled experiment. And that story I told you on the very first day about the women's hormones replacement therapy study, that was exactly a case where they had cohort studies which were saying that hormone replacement therapy might be protective against heart disease. But it turned out that confounding factors largely associated with socioeconomic status and sort of general medical awareness, health awareness, were almost entirely responsible for the protective effect. And when they did that randomized experiment, then they saw that the results were very different than what they thought. And actually, hormone replacement therapy was associated with an increased rate of heart disease and breast cancer. So you can do that in design, or you can do that in the analysis. That is, you go out and you collect your data, and there are these confounding factors, and you do things that we've been doing, like you stratify your results by a confounding factor. There are ways of taking these different odds ratios and combining them into a single number. We won't get into it. You can standardize age adjustment, which we talked about earlier. That's a way of correcting for the confounding factor of age. That's a huge deal. And you can do things a lot like age adjustment to deal with other confounding factors, or there's more complicated, sophisticated techniques like they used in the organics and eczema and atopy study, things called multilinear regression, which allow you to deal with several confounding factors all at the same time. Again, more complicated statistics. We're not going to be getting into that. They're kind of the bread and butter of the statistical analysis and epidemiology world. I want to just summarize a little bit some of what we've been saying. There's lots of reasons why you could see an association between two variables. Now, there's issues of size. In a small study, you might see an association just due to chance. So let's ignore issues of size. Let's assume we have a large study, and let's ignore measurement bias. So assume we're collecting good data. But still, we could have a causal association where the exposure causes the disease. That's what we want to know. We could have confounding. That's what we've been talking about. And there are other issues of bias. For example, there could be selection bias. We've selected a group of participants in the study that have differences between them that can lead to an apparent link. And these are the kinds of things we end up wanting to think about. I just wanted to draw a few pictures for you. We want to know if an association is causal. If your exposure causes your disease, possibly with some intermediate link in the causal chain, as we saw with the diet and, with the income and heart disease, where diet could be a link in the causal chain. So that's one option. We have this confounding factor option, where we thought that yellow fingers caused lung cancer, but it was actually due to the confounding factor of tobacco smoke. These two could be combined, where you could have some direct causal link and some confounding factor, making the story more complicated. And the other thing that can come up is bias. As we've talked about before, here's another example. If you look at an association between height and speed in the general population, it doesn't end up being very associated. People who are faster are no taller or shorter than people who are slower at running. But it turns out, if you look at the population of professional basketball players, then the ones who are faster tend to be shorter. That would make it look like being fast makes you short in some way, but actually it's because the only way you get to be a short professional basketball player is you've got to be really fast. You have to make up for that speed. So this is one of these stories people like to tell, which look at selection bias. So those are three different things that we think about when we're thinking about studies. We really want to know what sorts of studies are better. And these are our basic study types: our case control studies, our cohort studies, and our randomized controlled experiments. Thinking about everything we've talked about so far, we're going to put these in a hierarchy, where first I'm going to draw a line between case control and cohort studies. And case control studies have more room for bias than cohort studies. You certainly see some bias up here, but as we've already seen, you see a whole lot down here. A lot of measurement bias because you're collecting data from your control group and your case group, and those groups are different. There's also some room for selection bias because your control group is inherently being selected in a different way than your case group. So below this line, more bias. Above this line, still some, but probably less. Now we're going to draw another line here and say below this line, we have more confounding factors. And above this line, there's less room for confounding factors. In the perfect randomized controlled experiment, there wouldn't be any confounding factors at all. So you can see when you look at this that as you move up the page, the studies get more convincing. You do a better job of showing a causal link when you're looking at a randomized controlled experiment than a cohort study, and a better job of making a causal link argument when you look at a cohort study than a case control study. Often people like to draw more complex pictures like this one, where they move from the least convincing evidence, case reports. This single person had this thing happen. Studies that aren't in people, like animal trials or laboratory tests in petri dishes, cross-sectional studies, slice in time, ecological studies would actually go in here. Above this, you start to get into the studies that people will really begin to find convincing, and you see this hierarchy we've been talking about. Case control studies, weaker than cohort studies, weaker than randomized controlled trials, and above those, you have papers which look at several studies at once. You may remember the data that I showed you on abortion and breast cancer. That was data from a meta-analysis that was looking at a whole lot of different studies and combining them in various ways. And those are the most convincing because they're looking at more data and they allow you to get some information about the strengths and flaws of different types of studies and start to look for a consensus among all of them. And then over here are a bunch of things that this person wrote down that are just like not convincing at all. So that's our last slide on confounding factors. I'd like you to also work through the Epiville module on confounding factors, which has you thinking about these same questions some more. And we'll chat again on Thursday and I'll see what questions you have. Good luck, guys. Hope this works. Let me know, please, if you have any feedback for me on these slides and videos. I will certainly take it into account as I'm putting together next week's material, which will be on causal reasoning and how we decide whether we think we really have an exposure causing or protecting against a disease.